Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Spencer, and I'm one of the program managers in our external relations group. And this panel discussion today, I want to be congratulated on picking such a narrow topic. This is probably about as broad a topic as one can imagine. But but everything is sort of on the table here. I think you're going to hear some really interesting views, and I'd really like to encourage each of you at the very end to ask questions. And some of the things that we can think about are pretty broad. We know the breadth of software engineering, but there are other things like, what's the relevance of ICSE? What's the relevance of conferences and published papers? So I want you kind of to think about not only what these the speakers are going to present today, but also some other questions that you think are relevant to this topic. So today we're very pleased to have some great panelists, and I'll introduce them up here up front. First of all, there's Bill Griswold from San Diego. Then we have Jim Laris, our senior researchers. We have Lori Williams from North Carolina State. And we have John Pincus, another senior researcher here at Microsoft Research. So the order of presentations will be Bill, and then Jim Laris, followed up by Lori, and then by John. And we will entertain questions at the very end. So then again, welcome. Bill?
All right, thanks a lot, John. I want to thank John and Microsoft for inviting me out and for all you guys coming today. So what I wanted to talk about is a little bit of my experience in attempting to be successful in software engineering research, kind of at a high conceptual level. And my approach to being successful has been to avoid the obvious failures, if you will, the pitfalls. And so I'm going to tell you about some of those pitfalls so maybe you can avoid them too. And we can let Lori later take this down another level. So first we're talking about software engineering today, but there's a couple of general parameters that apply to all CS researchers, I think. One is that funding at NSF and DARPA are at an all-time low. And this is really suggesting, we have to rethink the way we do research because the funding available may be changing. Are we going to get that funding from different sources, or are we going to just do less? Are we going to go back to doing, pure theory? All good questions. And the second issue, again, we're all familiar with, is the short promotion cycles we have in academia and how that forces us to some extent into low-risk projects, which, of course, are often low-impact projects, and that's a kind of failure in itself. We're looking for high impact in our research, of course. So, well, with that in mind, what's unique to software engineering research? Well, I think of software engineering research as being the study of the effective creation of software. There's a focus, and it's not really a focus, it's really quite broad, a focus on artifacts, that is programs, the processes that create them, and the tools that assist in the creation of the artifacts within those processes. There's a lot going on in this area. But what's common is that there's an inherent practicality to the endeavor, right? It's about issues of scale. It's about real programmers and schedules, and ultimately about cost-benefit. You have to say, we spent this much money or time or whatever building this, and how much value do we derive from it in terms of contributions to society or profit or whatever. And so that's really sort of at the bottom of software engineering research. Okay, so I felt I didn't really have the answer to this, so I wrote to a bunch of my colleagues, and a few of them thankfully replied to me and said what they thought about this topic. So David Rosenblum talked about the lack of connection that many academic researchers have to real problems, and that they can get stuck in research eddies, improving each other's research results, but never really getting back to connecting that to reality, if you will, or some eventual path to reality. Of course, there's more theoretical and less theoretical, more practical research, but just some connection to reality over some period of time. And Kevin Sullivan talked about, sort of from a economic risk portfolio perspective, talked about putting all your eggs in one basket as being a failure mode. And Daniel Jackson talked about the advice that Butler Lamson gave him, which is to have one high-risk project and one low-risk project. Of course, remember, high risk was probably high impact, low risk is probably low impact. And if the high-risk project started to pay off, to kill off the low-impact projects. So that's kind of a portfolio management technique. Kevin Sullivan also mentioned this idea of failing fast, which is to say that if your project is going to fail, find out early, kill it off, and move your resources on to the next project. Okay, excellent advice. Daniel Jackson spoke to a failure that he had, which is the belief that all real systems have real research problems in them. And this may be true, but they may not be accessible. That is, the artifacts are too big and too complicated, and the groups that are developing them are simply too busy. And this is what he faced with the air traffic control system. And he had to move on to another project after wasting a considerable amount of effort. And in a related vein, Daniel talked about the difficulty of finding exemplars, which to him means small problems that capture the essence of real problems. And if you can work on exemplars instead of real systems, you can be very effective in your research because you're not dealing with all of the complexities, just the essential ones, and so you can have high impact at low cost. But he cited this as a really difficult thing to do. Okay, with these really nice thoughts in mind, I'm going to talk about what some of my problems have been over the last several years and how I address them. So one of my big problems has been attracting strong students. Students coming out of undergraduate programs typically lack good training in software engineering research. They have a lack of appreciation for what software engineering is about, and so they lack good intuition or motivation. And I've mostly been very successful in recruiting students who have been in industry for a while because they have that appreciation and some of that training. I've also had real problems in achieving experimental validity, which in a nutshell is what you might call realism with experimental controls. Okay? So I tried doing research inside SAIC, and that was awful because of the politics, and they changed their direction every day. And you move that stuff to your lab, and then you lose a lot of the realism, and that's a very difficult trade-off to manage in this research domain. And third is the problem is maintaining acceptable pace of research. Just you're building stuff, you're measuring it, and then you're analyzing all the stuff you've measured. It just takes an enormous amount of time, so the work is very slow, and that makes your risk in your portfolio look really high. Okay? So I thought about this for a while, and I realized, gee, this is all about scale. Right? I'm trying to solve a scale problem. Software engineering is principally a scale problem. And darn it, if to solve scale problems, you need scale. Right? PhD-bound college grads don't appreciate scale. They've been taking 10 to 15-week courses for 4 years. It's all about the short term. Right? It's hard to replicate scale in a research laboratory setting. It's hard to control it in the industry setting. And addressing scale requires a large research effort. You just can't do it by yourself in your office. You really got to build up a group. And that means more students, more time, more money. And we've already noted that we have a problem there. Okay? And of course, this is going to be especially hard on young professors because they don't have the contacts and the students and the money, et cetera. So this is I think it's a very challenging environment to do research. So what are some of the things that I did to solve these problems? Well, for attracting students, I got into the area of ubiquitous computing. And I started doing software engineering research in that area. And that's been somewhat successful, although very difficult, but I've certainly attracted a much broader pool of students. In achieving experimental validity, a key thing that no one would overlook here is the importance of collaborating with people in industry. And to use state grant programs like UC Micro to get some leverage out of that. And that's been very effective for me. The third is to use open artifacts and tools. And by open, I mean that you can plug in your analysis or whatever you've done into a real tool that people are using. And there's also openness in terms of source code and whatnot. And that's another way to kind of ramp up to the valid level more quickly than you might normally be able to. And for an acceptable pace of research, again, collaborating is a huge win, not only because you have more hands, but they're more specialized hands, and so they bring special talents to the table. And to build a hierarchical team of PhD students, master's students, and undergraduates so that they can help each other. And that also prepares the PhD students for a life in academia. And lastly, I'd recommend cultivating secret weapons. So this is my version of buy, don't build, right? Which is once you've built something, try to use it for a while. Don't just throw it away and move on to the next thing. So you might have a tool or a research method or some artifact that you've worked on for a long time, and those can really accelerate your productivity. So to get a little outside of the box here, a couple of last comments. One is, I think, that something that I've been impressed by what other people have done, and I feel like I've been less successful, is in asking the right questions. And the idea here is that a small project needn't have small impact. And one way to do this is to think about what things do I have to build, or what parts do I have to measure to get the research question I want to address, rather than just building and building and building and then say, well, now what's the question? Let's see if we can do an experience report. Right? Lastly, something I've been much more successful at, because I fail a lot, is making lemonade, which is looking at my own failures for research ideas. And suppose you're building a bug-finding tool, and it's not finding enough bugs. Maybe you found more than the other guys, but you were expecting much better. Well, why doesn't the tool find more bugs? That could actually lead to really deep insights about the phenomenon of construction and execution of software artifacts. It's actually more important than the tool itself. And so there's I think, a lot of rich fodder there as well. So that's all I had to say. And I will hand it over to Jim.
Is this working? Good. I don't have slides. The Microsoft people don't have slides in this panel. So that was a very nice talk, Bill. I'm going to give you a totally different perspective because I've taken a very different course than Bill. I was a professor for 8 years at the University of Wisconsin, and I came to Microsoft 8 years ago for a year's sabbatical, and I haven't left Microsoft. And the reason actually has a lot to do with this panel is that I came here to see how the real world worked. I didn't even necessarily really want to see it that close up, so I went to Microsoft Research, and I figured I could see a lot about software development inside Microsoft. And what I saw is this amazing opportunity that really wasn't being looked at by anybody else. That the Microsoft developers had these huge problems in terms of software development. Problems of scale, problems of complexity, problems of errors in the code. You name it. They're just a rich source of problems. And I looked in the university, and I didn't see very many people actually looking at these real problems. And one of the things that made me decide to stay here is that I thought about this, and I thought, I could go back to Wisconsin, I could be a professor, and I'd certainly have a lot more ideas about what I would do with myself and my graduate students when I got back. But then I asked whether it was going to be possible to actually do the kind of research that would really make an impact on these problems in a university. And my conclusion was no. And I think it actually goes to the point of this panel discussion. So, one of the issues that seemed to me to be the most pressing is software was developed by professional programmers in companies, and not just Microsoft, in a fundamentally different way than students in universities develop software. So, I don't know, those of you who knew me at Wisconsin knew that I wrote a lot of software at Wisconsin. And it was very widely used software, but it was academic software, which means that it's tiny in comparison to what people build here. It's simple in comparison to what people build here, or any other commercially successful company. And this is true of projects in universities, is that they're typically developed by 1 or 2 or 3 graduate students over a very short amount of time. They're only brought out in a small number of versions, and then they basically die away, or they go into the sort of place where they're no longer maintained. It's rare that a project actually persists for a long period of time and is supported by large numbers of people. And the question is, how do you actually do research with people who have no experience in terms of doing commercial software development? I mean, Bill said you get people who went to industry and came back. That's certainly a good way of doing it because they're much more aware of the actual constraints. But my experience was that there weren't all that many people who fit in that category. Maybe after the dot-com boom and bust, there were more people who had that experience, but there wasn't when I left the university. So that's one thing, is that the people who were in universities really didn't do software development the way in which commercial software was developed and didn't have any experience doing software development that way. Second problem was there was no software available to study in universities that was anywhere comparable to the software that commercial companies developed. I think this is less true now because of the open source community, but I'll get back to that in a minute. So, this is a serious problem. In a university, what are you going to study? Well, you could sort of write the software yourself and then study it, but that has some pretty serious experimental problems, particularly if you don't believe the people who are writing the software are the same as the people who would be writing it in a commercial environment. And if you don't write the software yourself, what do you get? Well, you know, when I was in university, we had the spec benchmarks, tiny programs on a commercial scale, 10, 20,000 line programs, sort of commercial cores, not really application, no GUI, nothing that made them particularly interesting or challenging to study. So the issue then is, what's the gist for it? Well, you know, you could go and try to collaborate with a company, and you could try to get access to their source code, and you could try to sort of do work. But those of you in the room who've tried that know that that's very difficult, is that companies don't tend to want to have outsiders look at their source code. You're an outsider, you're not part of the process. You don't really have the same kind of access you do in a company. And your graduate students probably don't either. And there have been examples of this being successfully applied, but they're few and far between. So I said I'd say something about open source. So I think open source has changed the equation a little bit. There are certainly large amounts of open source software out there, and by large I mean commercially equivalent applications. So I would say something like Linux, while considerably smaller than Windows still, is equivalent to the other Unixes in terms of size and complexity, and is probably comparable to Windows in those dimensions too. And there are other things, OpenOffice, the Mozilla browser and things like that, which are certainly equivalent to their commercial versions of the software. There are a couple of problems, I think, though. One of which is that the development process for open source software is different than the development process for commercial software. And you can argue whether this is a good or a bad thing, and I think it's an interesting debate. But, you know, from somebody observing it and having been part of the open source community for a while before I came here, the process is quite different than the way in which commercial software is developed. And so the conclusions you draw from open source software don't necessarily apply to software inside the university. The second problem I've seen is that very few people have ever taken advantage of this this large amount of software. I see very, very few real studies of open source software. Probably the most successful person I'm aware of is Dawson Engler, who actually was able to go in and do non-trivial things to the Linux kernel, both in terms of building tools, finding bugs, and doing sort of interesting, innovative work in there. And the reason that I think he was successful is, first of all, he's a great hacker and wasn't uncomfortable with 3 million lines of code. But second of all, he actually was from the operating systems community and so understood the domain of the application in the first place. And what I see a lot of going on is people saying, well, you know, I want my graduate students to work on this large piece of code, but, you know, they don't know where to get started on 3 million lines of code. They don't really understand the domain of it. They really are not equivalent to the people who are writing it. And so this is a challenging problem for, I think, people who want to use the open source software effectively, is that you need a large amount of leverage to actually take advantage of it. It's not enough that it's just out there on the web, but you actually have to be able to make effective use of it. And the third problem I saw is that there was not a clear path for results to flow from the universities back into companies. And I think that this is still an immense problem, is that most of the software engineering literature seems to be written for other practitioners of the software engineering rather than for people who actually do software engineering or software construction for a living. If you look at what people who do software for a living are aware of, it's not what's published in IEEE transactions on software. It's what comes out of various fads, to be quite honest. Things like extreme programming, which may have some very good ideas behind it, but that's what most people think of as being useful to them for day-to-day, because it actually is not so much concerned with experimental validity or anything like that, but is actually concerned with trying to solve the problems that people see in their day-to-day life. And I think that this is an immense disconnect between the software engineering community and the people who do software engineering. And, you know, one of the things that's been possible inside Microsoft is that we're very much in contact with the people who do software development. We talk to them. We don't necessarily always see eye to eye with them, but there is a much clearer path for technology transfer between Microsoft Research and the various parts of the company. And I think it's actually been very, very successful because there isn't this huge gap. We haven't been able to make, huge fundamental changes like to get people to use formal methods or anything like that. But, we have been able to change the way in which Microsoft develops software since I came here. It's really an immense difference in 8 years in terms of Microsoft's acceptance of formal tools, Microsoft's use of tools, Microsoft's belief that tools are actually going to make a difference in terms of software development and software quality. And I've seen that, and I think that that was only possible because the people who did it, in particular people like John, were inside Microsoft and seen as part of the same company, not people on the outside writing papers for other people on the outside. And so, I point these all out, not necessarily as criticisms of the software engineering community, but really as sort of my perception of why you have a very difficult task if you want to do research in this area. You're trying to study something that's very different from the environment in which you're in, and then you're trying to get your results to go out to a large number of people who are working in a very different world. So that's my comment.
I'm Lori Williams. Is this working now? And I'm an assistant professor at North Carolina State University. And actually, I'm hoping that my talk leads well off of the last two talks. What I'll be talking about is using industry as case studies in software engineering research and doing it from universities as a means for being a successful researcher. And my research group, we look at software process testing, reliability, and security. And we call ourselves the Software Engineering Real Search Group because ultimately, as a PhD student graduates, they work with real engineers on real projects. And the purpose is to have real impact in the industry as opposed to just influencing other researchers. And so what I'll be talking about today in my 10 minutes, as was said, there's all that, it's a broad range of things you can talk about with it, but that's what I chose to talk about in my 10 minutes of fame. And so what I'll start out with, there's lots of different kinds of empirical studies that can be done with software engineering research. And what kind of studies that you do really depends on the maturity of the technology. And so what I have here is stages of software technology maturation that was developed by Sam Redwine and Bill Riddle back 20 years ago. And it starts out with basic research and ends with popularization where a technology is actually into the practitioner mainstream. And in order to advance from one stage to another, you need to prove to someone, whether it be yourself or someone else, that you did a good thing. And so the validation step is an important step. But where you are in the maturation process depends on what you should be doing. For example, the first 4 steps, for the most part, you're trying to influence other researchers or yourself. So you're trying to influence the state of the art and other researchers. And so the kinds of studies you might do would be simulations, toy examples, student projects, experiments, where when you get to the last 2 steps, you're trying to influence the state of the practice and other practitioners. And that's really the area that I'll be talking about in my talk today. And so this is the area where industrial case studies are really important. Sam Redwine and Bill Riddle talk about these last 2 phases and talk about the need for good case studies to influence practitioners. Practitioners will adopt a new technology if people like themselves have adopted the technology and been successful at it. So it's important to get stories of people being successful out so that other practitioners will use the technique. And so one of the first examples of case study research that we did was focused on extreme programming. We wanted to look at whether extreme programming did help organizations be more successful. And we wanted to do some case studies. And so the first thing we did was look at the literature to find out what was going on with extreme programming. And as was said, a lot of things that we saw were qualitative case study experience reports from organizations that used it that didn't have very many quantitative measures. There were some studies done by academics, but every study measured something different. And so what we wanted to do was get a measurement framework so that we can establish a base, an evidentiary base of extreme programming. And so we developed a framework, which we call, for extreme programming, the Extreme Programming Evaluation Framework, which has 3 parts to it: context factors, adherence metrics, and outcome measures. And I'll give you an example of a case study, and I'll talk about what each one of them are. We developed a case study framework for extreme programming, the rational unified process, the team software process, and then most recently, Extreme Programming 2 was released towards the end of last year, which has a lot of differences. And you can see with all of those case studies, we ran them with different people, different companies. We ran case studies, so we have been working with organizations. Just to clarify, that this down here, this Microsoft down here, that's part of the template. That's not saying that we did a case study with Microsoft on Extreme Programming 2. Although we would be happy to do that. So here's an example that we did with Sabre Airlines. And this is context factors. So context factors is trying to say to someone who digests a case study, is this organization like mine? So if you have a small co-located team, the case study was done on. If you have a large distributed team, the case study is probably irrelevant to you. So it's trying to capture, what is this team like? What is this project like? Will this be relevant to me? We have lots of measures. This is a high-level overview of a Sabre case study, which there was 18 months pre-XP versus sustained use of XP. This was a small co-located team working on a GUI environment. Down at the bottom is a graphical view of the context factors. Five of what are considered the most important factors, which is how skilled are the people, do the requirements change, what's the culture of the people, the size of the team, and the criticality of a defect in the software. Those 5 factors were deemed by Barry Bain to be important factors that would say, is this team amenable to an agile methodology or not? And for the most part, this team is a small co-located team, and extreme programming should work well for it. Another thing that we do, which hasn't been done much before, is adherence. So did the team actually use extreme programming? A lot of teams might say, I do extreme programming, but when you start to say, well, do you use pair programming? Well, no, we do extreme programming, but just not pair programming. Well, do you do the testing? No, we don't do that, but the rest of it we do. And so if you peel away, you need to find out exactly what are they doing, really in any technology that you study. So we measure adherence metrics. And then the last are the outcome measures, which are business-related results, such as productivity, quality, customer satisfaction, and morale. And so, again, as using industrial case studies as being a way of having successful research from a university, there's some pros and cons to using industrial case studies. First of all, a good thing is a salience check. So, and Bill talked about this in the beginning, is tying it back to a real problem. And so if you're trying to do something and you can't get any industry to work with you, then maybe your problem isn't a real problem. And so the ability to get a partner kind of tells you whether you have a salient research problem or not. Even with that, finding partners can be difficult. Obtaining the measures can be difficult. And it can take a long time to run a case study. You need to have a whole release of a product, and you need it to be out in the field. So it takes quite a bit of time. As far as acceptance of research results, in general, with software engineering research community, they enjoy reading papers related to industry as opposed to student experiments. However, a case study is a n=1 experiment in some view. And so with that, sometimes people don't appreciate them quite as much. Industrial case studies support a movement towards evidence-based software engineering, which is building up a base to allow practitioners to base their decisions on research results. And finally, the main motivating factor is to have an impact on industrial practice. So that's it.
And so since I'm the only person on the panel who has the advantage of never having actually practiced software engineering in a university context, it's natural that I should go last. Some of the points I was going to make, I think Lori gave some really good examples from the standpoint of being in Microsoft research and trying to bridge the gap between research and practitioners. One of the things that's incredibly important is to understand whether ideas are likely to be relevant in practice for the problems that we face at our company. And there can be good ideas that are irrelevant. There can be ideas that are as yet unproven. There can be bad ideas. And in general, we have a lot more ideas just ourselves than we can actually investigate and get the product groups, our partners who are actually doing the development to investigate. So there's a very high burden of proof as we're looking at these things. We want some strong evidence that it's likely to be worth pursuing. So, you know, if there's large potential payoff and it's early stages, well, okay, we need evidence that there's likely to be large external payoff beyond more than just the it's possible. And the kinds of breakdowns that Lori talked about, these very detailed breakdowns of understanding the contexts, understanding the specific experiments or case studies that have been run, whether they're natural experiments or constructed experiments, understanding that and getting a deep understanding of how mature this research really is very crucial from our perspective on understanding, is this an area that is likely to be of interest to other people? And I think the same is true in situations where you're directly speaking to the practitioners, where there's not this sort of mediating organization. There, I think the burden is going to be even higher to convince them that this idea is better than the ideas they have themselves that they can't work at, and that they don't have the time to work on. And this is a huge issue, I think, in the field of software engineering today, that the time it takes to do these kinds of detailed analyses is not rewarded by the prestige of the publications, let alone the number of publications that you can come out with. This is something that all I can do is express sympathy, but observe as an outsider that there needs to be some way of using alternate publication methods, of working within to rethink the whole promotion process so that there's more incentive if the goal is to actually make an impact in this way, particularly with the late-stage research, that there actually is more incentive, or I'd settle for there being less disincentive to do this kind of work. But I'd actually like to turn things around and look at an area where I think academia has a huge advantage over industry in terms of software research, and that's the fact that increasingly the kinds of problems that we face in software engineering are really cross-disciplinary. They're not inherently only computer science problems. I think agile programming is a really good example of this in general, that if you look at a lot of the techniques, to the extent that they work or don't work, it's not as a manifestation of classic computer science principles. There's very important social aspects going on here, involving the sociology, the psychology of the programming teams. I think as we look at the more general problem of not just how do we construct software, but what software are we constructing? Is it the right software for its uses in context? You start to come to the realms where things like cognitive science and, again, sociology, economics, etc., are becoming incredibly important factors in all of these. And even a place like Microsoft Research, which has a relatively large research department, is woefully underinvested in these non-computer science areas when compared to a typical university. And so I think that the real opportunity, or a set of real opportunities for academic research is really broadening this notion of what goes into software engineering so that it's being done in conjunction with these other lenses. And it's not going to be easy to get closer to the code than you can in an industrial setting. As Jim points out, with open source, you can approximate that. As Lori points out, by partnering with industry, again, you can approximate as closer to code. So there's never going to be an inherent advantage there. It's important to take this dramatically different perspective, I think. So although this is a short talk, I really think that's the key towards rethinking these problems.
Okay, I need to find, where's my runner here with the microphone? He's not here. Okay, I'll do it. Okay, yes.
Though there has been emphasis on successful software engineering research, but the specific topics of doing in software engineering on which research can be done has not been emphasized too much. And for example, if I'm from India, and we have around $5 billion service industry, which where day in and day out they are developing various kinds of small applications to very large applications for most of the day-to-day activities. There are different groups of software engineers spread around geographically distant areas, and there are various issues that have come up in developing large products and delivering it on time and making profit, reusability, artifacts, and various other issues. And so I would like to see some light on what kind of issues you think would be useful there.
Well, I mean, I think this is a classic example of something that's really going to be amenable to an interdisciplinary approach. What are the, for example, in this particular scenario where it's in many ways it's the economics which are driving this, what are the different approaches that you want to take to reusable software and the value of reusability? Are our traditional notions for what it means for software to be reusable and the ways in which it's reused, are those just optimized for the old-fashioned within a single corporation for particular uses? Can we broaden these notions, perhaps with different metrics, and again, bringing in the sort of more, the different analytical techniques that you get from these social sciences might point to a way towards different approaches for adopting these problems, attacking these problems?
That's actually a very good question, something we should have probably addressed in our introductory remarks. I have a couple of ideas. I mean, to me, if I look around, the sort of most pressing need is the ability to actually write down specifications and designs for software in a way in which the practitioners, not just experts in a small area, can actually use these in their day-to-day life. So, particularly when you talk about software development over a wide area or in different countries, the ability to actually write down in advance and to do some analysis and design to make sure that it works before you go off and build it and before you have complicated contractual relationships is extremely important, and it's an extremely underserved area in the field. I mean, it's obviously been around for a long time, but it's underserved in the sense I don't think that there are any solutions that are widely acceptable or even widely known. And I think that that would be an excellent area for people to focus in on, because I don't see a lot of that work going on anywhere in industry or in academia.
I would like to bring the focus from software engineering research to software engineering teaching. So, for example, Ori, what she mentioned about building case studies so that you will be able to bring out certain issues in a very convincing fashion. That's a very good effort. Software engineering has traditionally been a very boring subject for the undergraduate students who haven't seen the real world, the real software development, etc. And then in the classroom, you're going to tell them about, this is how you should do, and then these are the millions of lines of code, and you need to use the configuration, control management, and all that. Okay, yeah, it's all good, but they're not really seeing what you really mean and why they need to really practice software engineering, whatever the processes or aspects in the when you're teaching software engineering. So typically, this is a course that is appreciated after they come back to school and tell them, like, at that time I didn't appreciate, now I understand what you meant by that. We conducted an experiment last year. I was teaching software engineering course at IIIT Hyderabad, India. What we did is we did an extreme step of conducting all the classes using just the case studies. These are not the case studies that you were mentioning about, but these are the teaching case studies, like Harvard Business School style case studies. So we worked with industry, like services industry, and also Microsoft, and then actually brought a problem, the real problem, to the classroom, along with the real managers who kind of manage that project. And then it kind of was really very well appreciated by the students So like this is something maybe, one way of changing the perception of the subject. So I would like to see your comments or any reactions to this.
I guess, the only one comment I'll make is that it sounds great, and I would encourage you to try, if these case studies are publishable so that others can use them too, that'd be fabulous. But I guess you're saying that you had real case studies from your local area and you actually brought the managers of those case studies into the classroom. Yeah, which is even better. But I think it would be great to have, just like Harvard Business Review has, a whole collection of case studies that can be used with software engineering students to present those kinds of classical large-scale problems. So all I could say is that's great.
Okay, we have a question in the back here.
Actually, could I just speak to that a little bit more? So I think this relates to the training and appreciation thing that I brought up earlier and why I want to speak to it. And we've talked earlier about students going off to industry and coming back, and they have the training and the appreciation. But I should be a little bit careful that there's research methods in software engineering that I'm looking for training in, as well as appreciation for the problems in software engineering. And I want to decouple them a little bit because the research methods are very different than developer methods, especially for the stuff that Lori just presented. You don't have to write a line of code to do her experiments, right? So, other disciplines have figured this out. Physicists use astronomy to inspire students. Mechanical and civil engineers use, beautiful bridge designs and things like that. And computer science is a little tough because a lot of the phenomena of computing are fairly abstract. You have to get into it for a while before you appreciate it. But we do have our, graphics and video games and beautiful visualizations and spinning atoms in space and things. And I think, there's a little bit of a bait and switch. You see the beautiful constellations, then you go study physics, and, you're reading, X-ray, traces on sheets for the next 40 years, sitting in the dark. And it's like, wait, that's not what got me into this in the first place. And, it's not like think of it this way. Does a future physicist have to become an atom to appreciate physics? Well, why should a computer science or software engineering researcher have to become a practitioner to appreciate the development of software? There's something a little, I think we have to be a little bit careful here and say, no, I'm not a software engineer. I'm a software engineering researcher. It would be inappropriate to say that. But I do have, certain skills and research methods. And that's what, we should inspire developer appreciation, but we don't want to turn all the researchers into developers. That's too expensive. It's one way to do it, but it's not the only way.
With all due respect, I somewhat disagree. I'd say that the software engineering researcher not having a grounding on what software engineering is in practice is sort of like a sociologist not living in any society, or a psychologist not being a thinking person or being self-aware, that we're not studying in software engineering, we're not studying the fundamental rules of the known universe. We're studying these complex social systems, and you have to have some experience of understanding the social systems in order to effectively be able to study them. Even if it's not the specific system you're studying, I'd certainly agree.
So I certainly grant you that, but a society of developers is a culture and a society. In fact, a lot of the most insightful methods in software engineering research today are anthropological methods. And those lend tremendous insights because the social networks that develop and the customs that develop, it all works out. And there is a deep technical component that needs to be understood. But that said, again, I'm going to come back and say, yes, I'm a member, as an anthropologist, a member of some society, but, that society over there just really seems so divorced from mine, and yet these people do research. So the question is, what connections do you need? And I think that, the experience that one develops over time, as a researcher and as a developer, because we all have done software development in teams, right? Just not necessarily commercial, but that's a different, again, it's one culture to another. So I think, it has the potential to work out. I'm not saying that no researcher should do this. Let's split 50-50. So, Jim said he stayed here, for these reasons, but he's still not a commercial software developer, right? He's still basically, academic researcher sitting a lot closer to the developers than he was before. And I think he's being pretty successful.
I want to tell you as quickly as I can about the experience of an academic scientist shifting in the other direction, working in the business world. So I took a job for a year as a CTO of a small software company that a friend of mine owned that has development offices ringing the planet. Dresden, London, Edmonton, Kuala Lumpur, Ann Arbor, Sacramento, Sydney, and Belo Horizonte in Brazil. And it was an interesting exercise, and I can confirm some of the things that I've heard you say. The first one is that the key problem I see as a researcher is developing ways to communicate at different levels of granularity. So Jim spoke directly to this. We don't have sufficiently good tools to communicate and choose our levels of communication. To give you an example is that trusted developers and team leaders working from Kuala Lumpur to Dresden can be effective in developing a complex piece of code that I cannot outsource to a team in India because I can't manage the level of abstraction and the communication. With that said, leadership in how to communicate and how to communicate cross-culturally within a single company is also essential. Speaks to the anthropology study. So there are some things that we've done. We had an anthropology student do a master's degree studying cross-cultural software engineering development that I can make available to people if you're interested. So, but the key that I found as a researcher is going back and forth, and we simply don't have sufficient tools to manage the granularity of abstraction.
We had a question up here, I believe.
Thanks. I'm from Indiana University. My experience has been actually somewhat frustrating, and I guess I'll share it with you and have you guys comment on it. I grew up in the database world, my undergraduate and graduate work and so forth, but I moved to computational biology and bioinformatics. And what I've discovered is while we were taught that lots of these methods are the only way to do things and this is how to get projects done, what we've discovered through several years now is that most of the things that we were taught don't seem to work in this area. I mean, there's many obvious reasons. One is that the scientists don't really have work at a company. It's kind of a loose confederation of who's doing what work and what's important. I'm curious, how do we make inroads in these sciences? And we've done a poor job, my feel is right now, in employing successful software engineering practices. What might we do? And I would say from an academic standpoint, even submitting research in terms of what counts as impact, you know, we face this sort of two-edged sword. The biologists don't really care if we get something running in a nice time complexity. On the other hand, the database people would say, well, look, this has all been figured out. I don't care that you can model stuff pretty successfully. So I'd like some comments.
So let me take that on. I don't know if you're familiar with the work that Jim Gray has done. Yeah. So for those of you who are not familiar, Jim Gray is at Microsoft Research in the Bay Area, and he's done a lot of work with the astronomy community, astrophysics community, and basically he's an extremely well-known database researcher who has come on and basically said to this community, you know, you have a tremendous amount of data, you're storing it in flat files, you're missing, you know, all of what's been learned in databases for the last 30 years. And he's actually gone and made it real by going and working with the people who have the data and showing them that if they put it into a relational database, that things that take, you know, pages and pages of Perl script can be done in a single SQL query. And I think that that's the way in which you answer one of your questions, which is how do you have impact on the scientific community? You basically have to show them that the products of computer science and software engineering are better than the way in which they've done things. And you have to be willing to sort of persist in spite of the fact that they see you as the equivalent to the guy who does the plumbing for their lab. But, you know, I think that if there really are advantages, then people will eventually come around to see it. And, you know, hopefully there are advantages in terms of the way in which we do things. Sometimes it's difficult, though.
I just wanted to add that, you know, the tech transfer process is traditionally very slow. They say 20 to 25 years. And you can accelerate that by, you know, some of the things that Jim just described, although I guess relational databases are about 25 years old. So,
Not the scientific world.
right, exactly. You know, the whole reason the supercomputers exist at the universities is to accelerate this process as well. But if you look at the way software testing is done today, if you look at, you know, the IDEs that we use, the you know, the software development methods, everything. All of those are 25-year derivatives out of academic research, and you just have to be patient. Jim earlier talked about, software process, XP. He mentioned that. When I first saw XP, I was like, oh, and this works because of this, and this works because of that. And I said, and that thing, that's wrong there. And then boom, 3 years later, it's gone because, somebody figured out it didn't work. And so, although you don't necessarily see the direct path, I think if you go back and look, you could actually find that, these methods and tools, do come out of the academic community. The best method of dissemination, we find it from the universities, is our students. They take the ideas out because people are too busy to read. And when things get, one person reads an article here and rewrites it there in a more, digestible form, stuff gets lost. I mean, I'm amazed. I do interviews and I read these things. I'm like, wow, what happened to my words? So, there's no substitute for somebody being there, and we really think of students as the ultimate dissemination tool.
Software engineering research is obviously focusing up to a certain degree on process, production of quality software, etc. That's an important thing, but I think it gives an incremental refinement or improvement. The question is, what is on the other side? The disruptive technologies. What do you think? What are those?
Sounds like a question for Bill Gates, not us.
It's a very good question. I mean, one of the things that was very frustrating is that for a long time here at Research, we were building tools to find defects in software. And we built a number of different tools in my group, some of which are extremely well known in the academic community, others of which are actually deployed in Microsoft products. And they're effective at finding defects in software. But at some point you basically say, this is a very frustrating way to go about this. If the goal is to produce better software, then finding the mistakes after people have made them is maybe not the most direct path to producing better software. And then you start asking the question, are there ways to produce better software, which, you start and try to more directly produce the software. And I think that approaching it from that way would be very disruptive. I mean, if you go back 20, 30 years in computer science, people were much more interested in these bigger picture, more aggressive solutions to the problems. You can find lots of conferences about programming languages for better software, or programming languages to reduce defects in software. You don't see that anymore. Instead, you see people focused on much more narrow technical solutions to problems. But for the most part, these smaller incremental solutions are not going to lead to huge major changes. And so, you see a lot of the benefit and the inertia are actually shifting to industry rather than research, perhaps because of the funding situation, perhaps because of the tenure cycle. People are less willing to sort of go out and take aggressive measures. And in fact, if they do, I think they have trouble finding places to publish them that are academically established. And I don't have a good answer to that. If I did, we would be doing it. But I think you have to go and be much more aggressive. We started a project inside Research called Singularity, which basically said, what would software look like if the goal was to produce software that was more reliable and forget about performance? And so we're doing things like writing the entire operating system in safe code, in the equivalent of Java, C#. And doing things like that and bringing in tools very early in the process and sort of changing the software architecture to try to provide more isolation between parts of the system. So things like that, which I think are very difficult to do on a small scale and very difficult to do in a university, but are much more likely to lead to big changes where you catch the errors earlier or you prevent the errors in the first place or mitigate the consequences of the errors as opposed to going and trying to find defects in software.
And I think one of the things that we've heard several different times here, which is a huge source of these potentially disruptive areas, is things focused on communications, both within the team but also with users. And requirements is, in some sense, a communication problem. It's not clear to me it's ever really been tackled as a communications problem. And this is actually an area where the differentness of open source development environments and their quirkiness and their distributed nature and the fact that everybody's doing their own thing is actually a virtue from the standpoint of understanding some of these communications issues. That solutions for there will actually apply in more constrained environments as well. So I think that's an interest, as Jim says, if we had more concrete ideas, we'd be off working on them right now instead of sitting on this panel. The other thing that I'd like to highlight is it a time to possibly start rethinking architecture more oriented around graceful degradation, particularly with respect to both security and privacy? The intrusion-tolerant computing field has some aspects of this. Are there other approaches? That's something where, as Jim points out, we can be giving up some performance. We can posit things like safe languages for the component construction. Are there new ways of tackling that would possibly let us get at the two things? One, real-world security guarantees. I mean, security guarantees of the kinds that people, as in users, actually care about. And then two, does this give a different way of looking at the composability problem, which is still essentially an unsolved problem in the general case?
I wanted to actually add one thing to what Jim just said, because I actually have a very similar thought about the or reaction to all this work in bug detection, in that it seems, oh gosh, if we could just have found those bugs in the first place. And of course, we know we can't find them all, and a lot of these techniques find stuff that just who would think this stuff up anyway. But it's become a fad almost. Everyone's doing it, right? And it's like, okay, maybe it's time to move on. Two comments. One is that the strength of the bug detection work is that it fits into a part of the software development process that researchers can get in, and so it's very pragmatic in terms of having real impact. But now what I'm starting to see is people are starting to take stuff out of that work and sort of push it up the software development chain. So they're starting to characterize a lot of what they're doing in terms of types. Well, once they're types, those things can be concretized in a number of ways and treated in different ways, not to find bugs, but to prevent them. And I'm starting to see several results coming out now. So it's you think, oh, this is we're going down the wrong path, and all of a sudden people have changed direction. So I think it's very difficult to look at the macro environment and all the activities going on and predict where it's going to go and how it's going to work out. And one of the key aspects to successful research in the modern world is that you have a community developing things. There are a lot of bets down on the table. Most don't pay off, some do, and as a consequence, we all move forward through some sort of stochastic process that's economically speaking very successful, even though it looks like a large investment.
But I mean, on the bug detection thing, on that whole area, I think this is an interesting area in that it wasn't actually driven by academic research. The recent flurry in academic research was actually in response to some commercial bug detection. I gave a 2000 ISTA talk talking about the specific dynamics that had at the time, I think, kept some of the academic work from having this influence, and I think there's still lessons there to be learned from other areas. As you point out, tracking what's going on outside of the research community and then trying to distill it. It's like the work that's happened after that initial commercial work is much more impressive from a research perspective and is leading to these deeper and more transformative changes. What can be learned in both directions, I think, is in general a good way for discovering new research areas.
But I want to appreciate everybody's input. The questions were great, and I think our panel did a great job here. So thank you very much.